This equation from high school is used in many video games to create the mechanics that makes them feel so good. Stick around and get a fresh perspective with examples you won't find in any textbook. Every video game you've ever played is powered on math juice. This video kicks off a new series where we'll break down the essential equations that power video games. We'll look at what they do, how developers and engines use them, and how they actually show up in many beloved mechanics. Contrary to what they teach in high school, here you'll see how these equations actually behave and how to bend them to suit your needs. It might come as a surprise, but behind the explosions, dashes, points, and jump physics, it all comes down to a handful of elementary functions and operators. So, not the scary kind of math. That's the kind of shit that I have to put up with, which is why I'm doing YouTube right now instead of working. Anyway, we'll start with the simplest, the basicest, and simplest function, the linear function. It might not look very exciting, but don't worry, we'll straighten that out by the end of this video. You may be surprised to learn it secretly drives everything from damage calculations to health bars, smooth animations, and even the way endless runners ramp up difficulty. It's kind of the hidden foundation of game math. Alright.
Enough talk!
Let's dive in. First, we'll define what a function actually is. A function is a machine that takes an input value and based on that input gives an output value. That's basically it. This machine, called linear function, is used to calculate a variable's value that is dependent on 1, 2, or even 3 other variables. Let's start with a quick and simple example to get our math juices flowing. Inside the game engine, calculating smooth health decrease or regeneration is usually performed through this equation, where t is the time passed and h is the decrease or regeneration rate, depending on whether it's positive or negative. For example, if your health is 20 and you start regenerating health at a regeneration pace of about 10 HP per second, then the equation will look like this. This means that your health is correlated when you stop regenerating. If your character loses health, then the health bar will drain smoothly according to a similar equation. Only now, h will reflect the bar draining pace. Notice that the h time t component is negative in this case. This being negative tells us that the health drops the longer you're taking damage, which is what we aim for. Calculating health points is a nice implementation, but there's more to this function than only this. To illustrate the next implementation, let's consider an example. Let's say that in the game your friend got pushed off the balcony of a crack house and broke both their ankles and they can't drive, so you're taking them out to buy some crack.
Boy, that escalated quickly.
Anyway, you arrive at another crack house and they immediately start shooting. Your friend is shielded by the casting, which acts like an armor, dropping the damage taken by 50%. So to calculate the damage dealt to them, the game applies a linear function between the weapon damage of the crackheads and the damage dealt to your friend. This is done fairly simply by taking the weapon damage and multiplying it by a half, which results in a linear function with a equals a half and b equals 0. Here you can see how the two variables, armor and weapon damage, work together to define the behavior of the dealt damage. The larger a is, the stronger the correlation between the weapon damage and the dealt damage. Your character, which sloppily wears a t-shirt with a mere 10% armor, means that you receive 90% of the weapon damage. So if you've been following along, you can probably tell that the equation to calculate its dealt damage is this one. In this graph, you can see just how much that armor is worth. The larger the weapon damage, the larger the difference between the dealt damages. Okay, we just saw what the role of the A parameter is, but what about the B parameter? Well, now let's assume that sometime during one of their cooking sessions, one of the crackheads actually managed to fuse some chemicals with their weapon, and now it has 5 points armor ignore damage enchantment. What do you know? To calculate the damage from this fella, all that is required is to add these 5 damage points as the B parameter. Notice that we do not add them to the weapon damage X, but add them separately straight into the output. From that, we can see that the role of the B parameter is to take into account the variables that ignore the multiplication by the A factor. It's what's called an offset value, which adds directly to the output. This is why devs love the linear function. One input, one output, two variables to describe their relation, and no funny business in the middle. It's basically the math equivalent of IKEA instructions. It gives a constant and simple relation with no changes in the middle, and everything goes on the same forever. In later videos, we'll discuss more complex functions that allow for different, more varying and interesting behaviors. The second scenario where games use the linear function is when they want to smoothly transition between two states A and B. Well, maybe not use A and B, so X and Y. Oh, maybe not use X and Y, use alpha and beta. Yeah, running out of letters is a known engineering problem. Anyway, so we want to transition between two states, alpha and beta. It's fairly similar to the HP example from earlier, but a little more explicit. There we just wanted to start from alpha and then go on until we stop regenerating or losing health, but here we want to explicitly go from alpha to another point beta. For example, if we're making a runner game and want the player speed to increase gradually along a part of the course, then we only require the start and finish speeds and the length over which this change will take place. You can see that with this information we can plot 2 points on the graph. We want to get from here to here, and the simplest way of doing that is by using a straight line. The line equation is, as we mentioned earlier, with A equals the end speed minus the start speed over the length, and B equals the start speed. This makes sure that your output goes through both of the desired points. This is basically that equation from high school, but now you can see and understand its meaning and its importance. Another great example of this is when games blend together two types of animations. Let's say you were away from keyboards or you're not moving right now, so the game displays an idle animation. When you start moving, games usually don't switch from idle animation to run animation in an instant, but rather smoothly transition according to, you guessed it, the linear function, which in this case looks like this. You can see this is the same equation from earlier, only in different dressing. This just goes to show you how powerful and versatile this simple function is, and how it pops up everywhere in video games. So, to recap, today we've learned about the linear function, how elementary it is in so many video game applications, and most importantly, how casting can save your life when buying crap. That's the linear function. Simple, rigid, but everywhere in video games. Next time, we'll move beyond straight lines and get a little curvy, where things will get way more interesting. Jump arcs, timed actions, trajectories, all that juicy non-linear stuff. If you've enjoyed this video and want to keep uncovering the math secretly powering your favorite mechanics, hit subscribe so you don't miss out the rest of the series. And if you've got a favorite example of linear math in game that I haven't mentioned yet, drop it in the comments and I might feature it in a future video. Until then, keep your line straight, your slope steady, and try not to get shot at the crack house. Cheers, guys! And get a fresh perspective with examples you won't find in any textbook.